All right, so we're going to talk through the answers to this group work here. So the first one said draw a graph that satisfies condition 1. That says that f of a is defined. And so we're just picking a random value for a here, and it's defined. And so that means we know we're going to need a closed circle somewhere. So just thinking ahead a little bit. And then it says, but not condition 2. And so condition 2 says, just to remind you, that the limit must exist. And so now that's not going to be true. So that means the limit does not exist. So there are probably a few different ways you can do this one, but basically we want the function to be defined, but the limit to not exist. And probably the easiest way to do that is put a closed circle there. And then to make the limit not exist, just have a jump. Okay. And so again, the graph could look very different than this, but basically at your a value, you need a closed circle somewhere on that a value, and the limit cannot exist. And so one good way to do that would be a jump. The other way to get the limit would be a vertical asymptote, but then it's harder to get your closed circle. So that's number one. Number two is going to be the graph satisfies condition 2. So the limit needs to exist, but not condition 1 or 3. And so we need the limit to exist, but the function to not be defined. And so if the limit exists, it needs to be doing the same thing on both sides, right? And then the function is not defined. Just make sure you don't put a closed circle anywhere, right? So for the condition 1 to be false or not true, no closed circle at A. And for the limit to exist, same thing on both sides, so approaching that same open circle. Okay? And this is called a removable discontinuity, right? It asks for the name of the discontinuity. So this is a removable up above on number 1. The fancy name for that one was the jump discontinuity. Okay? As long as condition 1 isn't true, condition 3 is automatically false, so we don't really need to worry about that. Number 3 says satisfies the first 2 conditions, and so now we need the limit to exist and the function to be defined, but condition 3 is not true, and so now we want the limit to not be the same as the value of the function. That's basically the same as problem 2. You get the whole so that the limit exists, but then you just put a closed circle somewhere. So now condition 1 is true, function's defined. Condition 2 is true, the limit exists, but condition 3 is not true. The two things are not equal. This is also called a removable discontinuity because you can simply redefine that point by moving that closed circle down. Okay, so that's 1, 2, and 3. Hopefully those went well. Now we'll take a look at number 4. And so number 4, we've got this piecewise function, and we want it to be continuous at x equals 2. And so that's the boundary between, those two functions. And so the first part of the function is pretty straightforward. It's x plus 1 when x is less than 2. And so here's 2. When I plug 2 into that top equation, I get 3. It's an open circle since it was x is less than 2, and it has a slope of 1. So the line's going off like this. And this is a parabola. That k is going to control how wide the parabola is. Basically, if we want the function to be continuous at 2, that closed circle from the parabola is going to need to fill in that point, right? And so how do we get it to fill in that point? Well, we know that when we plug 2 in, we have to get 3 out. And so I'm going to have k times plugging 2 in, so 2 minus 5 squared, and I want to get 3 out when I plug that in. And so now I just get this little equation. I get 2 minus 5 is negative 3, and of course negative 3 squared is positive 9. And so then I divide by 9, and I get k equals 1/3. And so when k equals 1/3, the parabola is going to look like this. Right, hitting over here at 5. And so now the conditions of continuity are met, right? The function's defined at x equals 2. The limit exists because it's doing the same thing on both sides, and the limit is the same as the value of the function. Number 5. So now we're finding and classifying points of discontinuity. And so that basically means we're looking for problems and seeing what kind of problems they are. And so for the first one, we're basically looking to see where the bottom is 0. And so it's just like looking for the problems when we were graphing rational functions in chapter 2, just looking at it in calculus terms now. So right away I see my domain restrictions are 3 and -3. And so those are going to be my points of discontinuity. Everywhere else should be fine. And then I just look to see which ones I can cancel away. X minus 3 cancels away, so that means this problem cancels away, which is, this is a hole. And so this is a removable discontinuity, right? This one cannot cancel away, and so that's going to be a vertical asymptote. And the name we give that is an infinite discontinuity, right? So 3, x equals 3 is removable, a hole, and -3, infinite. If you look and see what we did on problem B, is we basically had the same function, except we added this one little point. The point was at 1/6, comma, or 3, 1/6, when x is 3, y is 1/6. And so what is this doing? Well, it's the same analysis up here, right? We're still going to have an infinite discontinuity at -3. That vertical asymptote hasn't gone away at all. What is this 3 doing? It's basically, this 3, 1/6 doing, sorry, it's basically plugging the hole. If we go back to this function, I have 1 over x plus 3. When I plug 3 into the canceled version, I get 1/6. And so the hole on this one was at 3, 1/6. This point plugs the hole. And so there are no other discontinuities, right? No other discontinuities. And so only that one vertical asymptote. Last one, 5C. This is sort of like one of the ones when we were walking around the room on Friday doing those limit problems. This was like one of them. And so first of all, it says when x is 3, y is 0. So there's a dot. When x isn't 3, we're going to use this function. And the hint on the absolute value problems is to think about the two one-sided limits separately. So I'm first going to think about what happens when I approach 3 from the right. So x is a little bit bigger than 3, right? Well, when x is a little bit bigger than 3, oh, sorry, I just realized I put this dot in the wrong place, right? So sorry if that was confusing to you. The dot was at 3, 0, right? So ignore this here, 3, 0. So now we're looking just a little bit to the right of 3. Well, when x is a little bit to the right of 3, x minus 3 is positive, right? And we know what absolute value does to positive numbers. It does absolutely nothing. And so because I'm on the right, I can ignore the absolute value. And when I ignore the absolute value, I just get 1, right? And so what this graph is doing is anything bigger than 3, you just get 1, right? So it's just going along flat there. You know, try plugging in 3.1, 5, plug in a million, plug in 10, right? Every time you plug in something to the right of 3, you get 1. When we try the same trick to the left, now I'm plugging in things like 2.99, right? 2.999, something like that. And so now this thing in parentheses, or in the absolute value sign, is negative. And so the way I turn that negative is, the way I turn that negative into a positive is by sticking a negative out in front, right? And so now when things cancel, right, we're left with a -1. Right? And so what that means is, on the left side of 3, the graph's down here at -1. And so all that put together, right, tells me that what's going on at 3 is I've got a jump discontinuity, right? There's a jump here, jumping from one value to the next. Everything else is perfectly fine. It's just those flat lines, those horizontal lines, and so just one discontinuity. That's it. I feel like I sort of rushed through this. Hopefully I didn't misspeak too many times. If you have questions, I will certainly be happy to answer them on Friday. Thanks.